first off, I want to know who came to my talk last time. I know those two did. Okay, good. Anybody else? Okay, good. So there shouldn't be too many crossovers, but I did, for your sake, I did change the talk up quite a lot. So it's on a different topic now. The topic is size, and I hope at the end of this lecture you do understand that size does matter. Yeah, it is a very important aspect of biomimicry. Right. Before I start on size, though, I need to explain what biomimetics actually is. It is essentially the development of new materials, processes, structures, and so forth through imitation of nature. Why do we do that? Because nature has had quite a long time to evolve and develop these structures themselves. So we are still quite far behind in terms of our learning process. So the best source of inspiration is actually nature itself. Now, bio-inspiration is the mothership, yeah? And biomimetics pretty much sits inside this umbrella of bio-inspiration alongside its siblings, biotechnology, bioengineering, synthetic biology, and so on and so forth. You can include many, many things on that list, but I just included a few. Now, biomimetics is possible at various length scales. Yeah? I didn't say every length scale, and there's a reason for that. Yeah? Because we can look down to the molecular level, but if we start going lower still, then there's a little bit too much theory involved, and nobody's actually even attempted biomimetics at lower length scales than atomistic, one could say. Yeah. Now, there was a picture that was in the poster that I saw, and also on the front of this presentation. What we have here is, there's the pointer here. Right. Is this Peter Parker? Yeah, he's obviously quite jealous. He's saying that these dreamers have no chance. You've got a spider that's forming the Eiffel Tower. Has anybody seen the Eiffel Tower? Anybody? A few people, yeah? So it's quite big, isn't it? You know? But spider silk is the world's toughest material. Now, there was just a few months ago a paper in Journal of the Royal Society Interface where limpet teeth were actually shown to be the world's toughest material. Yeah, so they've actually knocked spider silk off the pedestal. However, there's another paper by Todd Blackledge's group I think it's in PLOS ONE, where they found a specific species of spider with a dragline silk that is at 350 megajoules per cubic meter. Yeah. Now, if you think steel has a toughness of around 6, high tensile steel, 6 megajoules per cubic meter. The difference is massive. Now, the Eiffel Tower is made of steel. So, do you think we can make the Eiffel Tower out of spider silk? I want to ask you. What do you reckon?
Yes.
Yes, okay.
From the rigid enough.
You think so?
Rigidity.
But it's toughness. It's actually stronger than steel as well. It's stiffer than steel as well. Yeah, so...
With rigidity, you could build a structure. I mean, it's not just build a tensile strength with it.
Okay, this is good. He's using, yeah. Keep going.
You scale the spider's web up.
Right. Okay, very good. I'm in a good audience, obviously, you see. So, first off, I'm going to explain the structure of silk, yeah, and then we'll go back to rigidity, which is a very important concept, yeah, and scaling, actually, comes later after rigidity. So, all right. So, basically, dragline silk, yeah, is made up of 5 different layers, but it's really this core inner layer that's important here. Yeah, this is the structural component of dragline silk. Yeah, and if you look at the structure, you have a very soft, malleable material, yeah, which is proteinous material, which is reinforced by these beta sheet nanocrystals. Yeah. Now, nanocrystals, they have a high surface area to volume ratio, and they will do a good job, essentially, of toughening up the soft, malleable domain. And these beta sheets, they're basically polyalanine units that are bound together by secondary interactions. These interactions are hydrogen bonds. Now, do you know how strong a hydrogen bond is? Not very. Yeah? It's not, is it? It's about how many kilocalories per mole for like 5 to 20 typically. Yeah. If you have CC bond, a covalent bond, we're talking about 350 kilocalories per mole. You can go halfway, pretty much, if you have a fluorine-based hydrogen bond, then you go up to 160 kilocalories per mole. But with these ones, these are OH hydrogen bonds, you have like 5 to 20. So it's not very much, is it? But if you have like loads of them, yeah, absolutely loads of these hydrogen bonds, then you actually stiffen up your structure, yeah, number one. You also have a degree of self-healing. So as these things, if you pull spider silk in tension, yeah, you'll have shearing between the molecules, but as shearing occurs, you'll keep reforming those hydrogen bonds because they are not, you know, actual connections. They are in negative space, so they will keep reforming, depending on the speed, of course, as you keep shearing this material. So you have self-healing that goes on with spider silk as well. Now, tension, very important concept. Here we have long molecules, yeah? So this is a long molecule, it's similar, yeah? It's geometrically stable if I pull it in tension. This is tension, yeah? But is it geometrically stable if I push it in compression? Not really, you see? So if I compress it, all of a sudden, the world's toughest material is kind of squishing and becoming like a concertina. And that's conceptually similar to what happens if you were to compress an entire drag line, yeah? If it doesn't buckle as the drag line itself, then internally you will get molecular level buckling, yeah? Which means, of course, that Tarzan would love this material, yeah? Because he's pulling, he's swinging, yeah? But contrarily, Vlad the Impaler would probably have questioned the immediate benefit of, because he's impaling, so he's compression. Do you see what I mean? So it's a different scenario. Now I know what's going through your minds right now. You're probably thinking to yourself, but hang on a minute, yeah? Didn't Vlad the Impaler use wood? He didn't use spider silk, yeah? He used wood, and he managed, and isn't wood also completely and utterly a biopolymer made up of long chain molecules? Am I correct? Yeah. So how come he managed to impale? Well, there's a difference here. If you remember, silk is lots of stiff nanoparticles, yeah, beta sheet nanoparticles that reinforce a soft matrix. Whereas with wood, you have a lot of cellulose, and in the case of wood, it'll be 88 to 95% beta crystalline. So it's a very crystalline structure, which means that it'll be very stiff. Yeah, and thus, you know, you can impale, yeah, number one. Number two, the other issue is that it doesn't grow in only one direction, yeah. You'll have one axial direction, but then at the cell wall level, you'll have interweaving of the cellulose strands. They'll change direction in different layers, in the different secondary layers, that is. On a macro level, yeah, you'll actually have xylem vesicles going in one direction, but then you'll have radial vesicles going in a different direction, which reinforces the structure in a different direction. So wood is very different. It's very, very crystalline, and you have this directionality, whereas with spider silk, you're drawing this thing out. It's coming out of the spinneret, so it's all being pulled, so it's a single direction composite in that sense. So, but if you were to compress wood enough anyway, or even to a little bit, because it's got long molecules, yeah, it will still have molecular buckling followed by micro buckling, and you'll see this. You can just take a piece of wood, take a hammer, and just gently hit it, and you'll see little micro buckles in the grains. You'll see that, yeah. But of course, micro buckles lead to macro buckling and then complete catastrophic failure eventually. So Vlad was lucky in that sense that his victims were not heavier than they were. Now, another problem here is volume. Yeah, if I wanted to make a rope for Tarzan, I mean, how much web is there in a spider web? I mean, how much silk and thread is there in there? There's not very much, is there? So, you know, and that's just Tarzan. What about all the other Tarzans who also want that rope once they see him swinging? You know, there'll be lots of people who want the same thing eventually, and this is reality. You know, this is one person gets a new iPhone, everybody wants a new iPhone. Yeah. So what are the options? How can we? And this goes back to what you said earlier about volume and production, isn't it? You see, what are the options? I'm going to give you 1 minute to discuss with the friend next to you, yeah, what your options are to scale up this problem of volume. Just think quick. All right, that's good. that's. All right, done. So I heard from these guys, spider farms. Hang on a minute. Ta-da! Now, if you see the smiley next to the spider farms, yeah? He doesn't look completely happy and he doesn't look completely sad. Does anybody know why? Like what? Yeah. Okay, he's scared of spiders, that's the reason, you know. But no, basically scientists will tell you that you can't farm spiders. Yeah. But I don't completely agree. Yeah. And the reason I say that is because we have a spider silk farming project going on in East Africa at the moment, and we have some kind of success. One of the problems with spider silk farming is that they are cannibalistic. So spiders are cannibals and they will eat each other. And a second problem is that they're territorial and they have big territories. Yeah? So this makes it quite difficult to farm spiders. So I have a story about this, how this project in East Africa started, because I heard a rumor that there were a group of mothers in East Africa who had started farming spiders. Yeah? So I took the plane from Finland to East Africa and we started driving. I was with my friends Stan and Silas, started driving around hundreds of kilometers chasing this rumor. Yeah? And then we reached this village. And when we got to this village, yeah, there was a Bombyx mori farm there, and they were growing Bombyx mori silks. Yeah? These are silkworms, right? No spiders though. And no mothers. Is the other thing. There were no mothers and there were no spiders being farmed, right? So anyway, I thought, well, I've made this massive trip, yeah, to find this, you know, to search for this rumor, and now I find it's not true, so I might as well just fill my suitcase full of Bombyx mori silks. And I thought, I'm done with this. But then, of course, I stand out like a light bulb in Kenya, and the villagers came and they started asking me what I'm doing there, yeah? So I explained the situation, and they said, oh, but the insect farm is just 2 kilometers down that way. So I thought, you know, we've gone 700 or so kilometers already, yeah? What's more, what's the problem with going 2 kilometers further? So we went there, and lo and behold, there were these mud huts where they were farming not spiders, but all sorts of insects, yeah? So their speciality was farming insects. So I explained the situation to them, and then one guy, Danish Olero, came over and just said, I can do it, yeah? So I left him to it, you know, we made an agreement that, you know, we could just keep, you know, contacting each other and like so forth. And then I phoned him up about half a year ago, and he said, I've done it, yeah? I was like, oh yeah? What are you using? He said, I found an aggressive venomous spider, yeah, which has a small territory, but makes a really thick web. Yeah? So he started farming, yeah, these small spiders that are quite aggressive. They're venomous as well, but they make very thick webs like a cage around themselves. So their territory is small as well. So I'm going back in August this year, and let's see, you know, how successful. You know, maybe we can prove the scientists wrong. Yeah. And also the scientists have only been looking at, I think they've only been looking at orb weaving spiders. They haven't touched on the aggressive venomous ones for some reason, you know. Okay. Another way is recombinant silks from bacteria. This has been done quite a lot. Does anybody know anything about this at all? No? Okay. So basically you genetically engineer bacteria and then they can produce recombinant silks. Yeah? One of the issues with this is that if you think the dragline proteins for MASP1 are about 300 kilodaltons. Yeah? So these are long, very, very long proteins. Generally, recombinant silks are around 60 kilodaltons max, which is, quite small. We don't have the same characteristics in the recombinant silks as we see in native silks. It's another problem. There's one paper that came out just about, I think, a month ago. It's a group in Germany. So, stress and strain. Does everybody know what that is? No? Probably? Okay, stress is proportional to force. Yeah, so you can imagine force. Yeah, linearly proportional. And strain is proportional to displacement. Yeah? So, or extension. Okay, so if you understand that, then this is quite simple to understand as well. And typically, a curve for silk will go like this. Yeah. And then the toughness, G, is toughness, is the integral of stress by the change in strain. Does everybody understand what that means? You answered this last time, so I'm going to go back to you. Oh no, okay. Engineers then. Engineers will tell me what this is. Right, good. So, this basically relates to the mechanical energy that's absorbed by your silk, okay? Now, in the case with the new paper from Germany, it kind of goes like this. Okay? Who can tell me what the problem is here? I mean, it's great. They got the same toughness. Yeah, so G for this is equal to G for that, approximately. Yeah? Yeah. The strength is different. Yeah? The modulus is different. The energy absorptive capabilities is the same, which is great, and it's a huge leap forwards. But we're still not getting the same characteristics as native silk. And at the end of the day, that's what we're trying to mimic. Yes.
So we don't have to come back to it. It's that whole self-toughening curve, flip in the middle there.
Yeah, basically, this would probably, it hasn't been proven, but most probably be down to reformation of hydrogen bonds. Yeah, or realignment of polymer molecules, or, and this is the theory that I will go with most strongly, is, just get rid of this if that's okay. Or you'll notice there are semi-crystalline domains in silk. Yeah, so if you have this kind of structure and you've got crystalline domains, then you have some unformed silks. They're misoriented as well, so not all of them are straight. Yeah, some of these beta sheets will be actually at an angle, so these will probably be lining up at this stage, and then strengthening, and then unhardening. Yeah, and then these will probably also be lining up as you pull this in tension. Yeah, so you've got these numerous possibilities for what's happening. I think the group of Fritz Vollrath in Oxford University have spoken about the orientation of misoriented beta sheets in the meridional direction of silk during tension. So I think that's probably the more likely scenario, but I don't think anybody's actually evidenced it yet. So okay, so that's one problem there with recombinant silks, still far behind. Nature, see, I tell you, nature is far ahead of us still at the end of the day. Then we've got biomimetic polymers. Now this has got 2 thumbs up for this one. Yeah, there have been a lot of attempts to form crystalline, semi-crystalline and amorphous domains in manufactured polymers. The group of Hammond did a good job in 2008. She's in, I think, either Harvard or MIT. And they actually have used polyurethane, as their templating polymer. So I think that would be another way of going about it. However, of course, with synthetic polymers, they're crude oil based, they're not biodegradable, so there are other issues that come about through using synthetic polymers. So what else can we do?
Genetically modify spiders.
So it's funny you should say that, because I had planned to say during the silk farming part that we could modify the spiders to take away their aggression or their venom.
There's also sociable spiders, stegodophilus spiders, which are a group of 10 or 12 spiders that all live comfortably together and create huge nets of
Right. So then this is what we must do then. Genetically modify spiders. I agree with that. I completely agree with that. Anything else though? From an engineer's perspective, perhaps. Yeah? Harvesting. See, what we're doing is we're focusing so much on the actual native silk. But you see, silk has many qualities. You see what I mean? So, okay, this has moved a little bit. Sorry about that. But I can give you an example from some of the work we've done. Basically, I think we can focus on specific qualities when it comes to biomimicry. Yeah. So, silk has numerous qualities. Yeah. Very, very many qualities. But if we focus on one, yeah, and we mimic that, and then we use that, then we have greater potential in manufacturing at a large scale. You see what I mean? So this is a story on our work with flagelliform silks and bacterial nanocellulose. So bacterial cellulose, we've been using those for a long time, at least 3 years now, for wound healing, developing wound healing materials. We get our bacteria from Indonesia, the Acetobacter. They produce the largest quantities of nanocellulose, and this is like 98 to 99% beta crystalline cellulose. It's very pure. It's really good stuff, basically. Flagelliform silks now, silks, they have different glands. Spiders, they have different glands, yeah? Like about 7 different glands. Depends on whether you're male or female, as to whether you have 3 or 4 and so forth. But each gland produces a different kind of silk. So dragline is the strong one. Flagelliform silk sticks on the surface of radial threads, and it has a sticking potential, and it's also more extensible than dragline. So what we did is we started by identifying the key segments in the flagelliform silks that give rise to stickiness. So we're only focusing on stickiness now, yeah? One specific. So once we identified those, we isolate the amino acids and apply these as bioglues to bind the bacterial cellulose, yeah? And our result is that we, approximately double the strength and stiffness properties of these materials, yeah? And it's such a simple thing to do. You see what I mean? So we're actually putting the paper for that together now. You're getting stuff that's hot off the press, by the way. Yeah. And what's happening, essentially, is that the regions of flagelliform silk that toughen or cause stickiness, so to speak, are the ones that form hydrogen bonds most easily. So you're looking at thin ones that don't have large rings sticking out of the side. You're looking at the ones that can align easily, that are relatively malleable, so alanines, glycine, that kind of stuff. And when we stick them in between the bacterial cellulose, they form mass hydrogen bonds between the cellulose molecules, and then you have this increase in strength and stiffness. So, double. I skipped this slide by mistake, sorry. Now, if you look at where we're at, here you got dragline silk. This is an Ashby plot. So this is specific stiffness, and this is specific strength. So specific stiffness, it basically is the stiffness divided by the density, and the strength here, specific strength, is the strength divided by density. So you're looking at the specific mechanical properties with respect to weight, which is an important engineering parameter. Yeah. Now dragline silks are around here. Yeah, so we actually have stronger, with respect to weight, materials now than dragline silk, but our stiffness values are not anywhere near we're about 10 times, maybe more, lower in terms of stiffness. But at least we managed to improve the quality of strength. And that is down to stickiness. That is down to hydrogen bonding. Yeah? Okay. So what can we say? This is the first size level that we're talking about, molecular biomimetics. Scaling up from molecular to macro is possible given an understanding of context. So Tarzan, yes. Vlad, no. Yeah. Scaling up could be problematic in view of volume output, and then more so in terms of actually manufacturing these things. Like I said, dragline there's a very specific manufacturing process with this spider. It's pulling this polymeric dope out of it's reeling it essentially. So there are a lot of shear stresses involved there, and the alignment of the polymer molecules is very important. And the last thing I can say about molecular biomimetics is that it may be more feasible at present to focus on specifics in order to upgrade composites, for example, rather than trying to recreate the native material itself. So nano is the next level up from molecular, and there are many different examples of nano materials in nature. Yeah? So biosilica of diatoms, they are porous, nanoporous nano cages made of glass essentially, and they form these protective exoskeletons around diatoms. Nanospatulae on gecko's toes, they're actually a good example of dry adhesion, yeah, and they adhere through van der Waals interactions. Nanoflakes, surfaces of butterfly wings, we have iridescence, protection, self-cleaning. Nanoparticles and plates, shells, corals, sponges, there for structural support. Nanofilms, you find these in waxy leaves, again, self-cleaning and protection. Nanospikes from the cicada wing surfaces. There's one type of fly in Australia which has these nanospikes on its wings, and the bacteria cannot grow on the wings of these flies. So there are many examples in nature, but what makes nano so special? Does anybody know? You see this thing here? Okay. This is not nano, this is macro, of course. We have a surface, yeah, and we have a bulk. All right? So the surface properties are very different to the bulk. Yeah? Does anybody know anything about Gibbs, free energies and that kind of stuff, or not yet? Okay. So the surface properties are different to the bulk, and that's because they have a different interface. Right? So the bulk is surrounded by its own type of material. Yeah? Now if I start bending this or pulling it, what dominates the properties of this material? Surface or the bulk? What? Bulk, right. Because the bulk is, volumetrically more. And if I start shrinking this down and down and down and down and down until it's super thin, and I get down to the nano level, all of a sudden we'll have a situation where the surface and the bulk are pretty much even or close to. Yeah, it doesn't have to be exact, but close to similar. And in fact, in some cases, the surface might actually be greater than the bulk. And the situation you have there is that nano doesn't know whether it should behave like molecules or whether it should behave like bulk. So molecules are they're quite malleable, they're interacting a lot. Yeah, if you have a bulk material like this and I put it on the table, yeah, I can pull that off quite easily because the bulk stops or prevents the surface from easily coming down and sticking to this surface. But if you have a nano material, then it can quite easily just start sticking at the surface or repelling, or it depends on the specific qualities of that material. So it's a very special size range in that sense, and it can't thus be scaled up and it can't be scaled down. Yeah? And nacre is a good example. It's a simple example of a difficult problem. Yeah? So we have abalone shells, yeah? And if you look at these in detail, You'll see that they are layered structures at the macro level, then they become layered structures at the micro level, then they become layered structures at the nano level. So at the nano level, you see plates, nanoplates of aragonite just popping up on top of each other like this. And what that means is that instead of fracture being able to go straight, I'll draw it on the board because it'll be easier. Instead of fracture being able to go through the material like this, yeah, it has to go through the material like this. Which means that the fracture energy is increased somewhat because you have a longer, more unfracturous path to take. And most of the studies on mimetics, and there's quite a few, they actually stop here. So you'll see a lot of mimetic composites. They are made up of kaolinite particles, and they are glued together by organics. But they're stopping here because we have another attribute, or another two attributes of nacre that we can't yet mimic. One is this, that each of the plates, they actually interlock with themselves. They grow into each other. So they will do this. Yeah? So they're actually attached. They're attached by mineral bridges. The other thing is that you have these on the bottom and the top of each plate, you have nanoasperites. Yeah? So they'll be sticking out of the plate like this. And that means that you can't easily move these things in a shearing or slipping direction either. Yeah? Which means that the energy required then to fracture at that level is going to exacerbate a lot. Yeah? So this is a big problem. It's very difficult to actually to try and manufacture that. Again, nature is quite far ahead of us. But this is not exclusive to nacre. Nacre is the one studied the most because it was one of the earliest ones where these nanostructures were discovered. But of course, pteropods in their shells, they all have nano fibers like these that are T-shaped and L-shaped, and they interlock. And again, then to break the pteropod shell, you have to break these mineral-based interlocks. Beetle forewings, when they attach to the carapace and the carapace closes, they'll have these hairs, yeah, nano hairs that will prevent shearing. Yeah, they can open this way, but they can't easily move this way. So that makes that means that the forewings are always in place. They're always in the right place when they're enclosed within the carapace. Diatoms, you've got nanosutures. Do you know what diatoms are? Anybody? These are like these microalgae that form perfect glass cages around themselves, but they actually have joints as well. And these joints, they call them sutures, and they're very, very symmetrical. Yeah, this is one of the amazing things with diatoms is the symmetry of these things. And check it out. Just Google diatoms when you leave the room. Yeah? Because if there's anything you leave with from this lecture, it's just this word, diatom. Because this is I think that's the future, is diatoms. Yeah? But if you imagine now, at this scale, there are interactions happening here in the bulk, but there are also interactions happening here at the surface. And of course, these structures are most likely optimized to resist force, yeah, and to resist fracture. So the interactions at the surface is probably not a repulsive interaction. It's more likely to be attractive in that sense. Now if we look thus at the interfaces must be key. Yeah? If the interface moves, the bulk moves. Yeah? If it's something as big as this, that doesn't really happen. Yeah? But with nano, that happens. Here we have one of the simulations that we have, that one of my students did. We have this nanocrystal. This is a protein, which is why we have these arrows. These are extended beta sheet forms. So this is a crystalline region, and this is an amorphous region. And in between, you see that it starts leaving crystalline and starts becoming, amorphous, or the amorphous starts becoming slightly crystalline. So you have this mixing at interfaces, yeah, as well, which will extend into the crystal as far as the bulk will allow. So the relative molecular motion in the bulk will also, in that sense, determine how this interface will actually react. You see? So it's very interesting in that sense as well. And this is currently something that we have under review with physical chemistry, chemical physics. It's a RSC journal. So again, like I said, you're getting hot off the press stuff. It's under review. Now, some things happen only at the nanoscale. Superhydrophobicity, self-cleaning, that's another thing. Happens only at the nanoscale. If these, you see here, how this works, you have nanostructures on the surface of a leaf. If you, for example, it's like lotus effect, right? You'll have droplet of water that can't wet the surface. And when it can't wet the surface, it'll roll off and it'll collect some of the dirt off the surface, and then it'll take the dirt off the surface of the leaf. So that's why lotus leaves are self-cleaning and they don't have dirt on them. Now, if we were to scale down to a molecular level or scale up to a macro level, we have wetting. So the only way that that will work is if the protuberances on the surface of the leaf are at the nanoscale. Same with butterfly wing iridescence. You see all the beautiful colors here? Does anybody know what the names of the pigments are? They're on the surface of these butterflies. No, because they don't really have any pigments. This is the thing. The colors you see are through these diffraction gratings. The structures of these gratings change, yeah? And with these minuscule changes in the structures, the nanostructures of these diffraction gratings, you'll actually have different phases of light coming out in different sort of, at different intensities. And as a result of that, you see the different colors on the back of a butterfly wing. And this is iridescence as well, so it's kind of shiny and glittery in that sense. So this is something that, you can't scale up and you can't scale it down, right? So it's tricky. So what can we say about biomimesis at the nanoscale? It is unique in its structure and behavior with the surroundings, of course. We've ascertained that already. Successful scaling up or down is unlikely based on our current understanding of these structures. Maybe in the future we'll know something different. Maybe in the future it's possible. Mass manufacture at the nanoscale has been achieved, for the more simple structures like superhydrophobic structures or anti-reflective coatings, that kind of stuff. But manufacture of more complex structures like iridescent structures, diffraction gratings, is very difficult. You can use layer-by-layer techniques, perhaps. You can use atomic layer deposition techniques, but these are very slow techniques, so mass production, it's not going to happen. Now, I'm going to stop with the size scaling stuff there, because I'll just show you some of the stuff that we do in our group. And the reason I show you this stuff is because we work at every length scale, from atomic length scale right the way to superstructures. So one of the things that we do is coral and sponge biomimicry, and basically we try to create composite materials that use the crystal engineering background, so to speak, of corals or the spicules that you'll find in sponges. We try to artificially manufacture those through chemical methods, basic precipitation reactions as well, or through biotechnology. That's another way we're doing this. And we have 3 papers. This one is currently in revision, but there's only a few revisions to make, so that'll be accepted, I think, within a couple of weeks. Then we also work on bio-inspired biomaterials, and I already spoke about the bacterial cellulose stuff we do. We're also working on synthetic biology in relation to biomaterials, because one of the things we try to do is combine different types, the specific important features from different types of silk together, to see if we can get the perfect silk for the application that we need. Then we also work a lot with diatomes, drug delivery, biotech, synthetic biology as well. This is a paper that I submitted a few weeks ago, and I got a message this morning saying the required reviews are complete, so I'm hoping that, they say accepted, no changes, but it probably isn't going to happen that way. But yeah, we basically managed to skeletonize insulin, using a diatome-inspired skeletonization approach. And this is good for drug delivery. The insulin is more stable if you can skeletonize it, rather than if you load it into a pre-made particulate. Yeah. So, and it's also faster. I mean, we're about 20 times faster. If we create this in a precipitation reaction, this is like about 20 times faster than the fastest of the drug loading methods. Because they actually have to manufacture particles first, then they have to, put them in like different substrates so that they functionalize the inside, so increase imbibition and that kind of stuff. So this is super fast. Then also we've been working a lot on dragonfly wing inspired superstructure engineering, and we found this is one example that's this currently under review at Materials and Design. We have one paper already in ASD, but we found this one libellulid dragonfly. It's Crocothermis cervilia, and it has a really weird joint just underneath the arculus. Now, and this joint is like a cross joint, and it has very soft resilin in between chitinous veins, and that's typical for many of the joints anyway, but this one goes like this, so it goes through another joint. It's like a bolt going through two pieces of timber. Yeah? So we just mimicked the actual softness of the glue and applied it to trusses for bridges, and for big roofs and so forth, and we actually found that we can quadruple the toughness. So this gives us insight now how that, you see, the dragonfly wing, it doesn't break. It's flapping 30 times per second, but it doesn't break. So for us, this is like a solution to earthquake engineering seismic problems. So then mud skipper biomechanics and robotics. I won't go into that too much, but this is awesome. They sit in trees. These are the, when I found these guys sitting in trees, they're fish. They're fish, and they sit on the branches of trees like this, and then when you come, they panic and they jump back in the water. But they can actually move, they can climb vertically and all sorts of things. They're amazing. Then bioglue technologies, I spoke a bit about that already. Silk engineering, I've spoken a lot about silk, so I won't go into that any further. Whale biomechanics, suture biomechanics, and now giraffe flight mechanics. So this is stuff that I'm doing now in collaboration with UCT for a while now with Anusia and also Professor Daya, but now also with Rob with the giraffe fight mechanics. This is one of my, this is a good thing actually, because I do a lot of like boxing and stuff anyway. So fight mechanics is no chance. I think I'd be my last fight. And then of course functional morphogenetic timber architecture. So there we're applying biomimicry in the context of aesthetics and art, architectural art, but also we're making it functional. So that pretty much concludes everything. Oh no, one more. Sorry. We're also looking at anti-HIV, anti-cancer compounds. We're trying to characterize those. We found lots of different, very interesting compounds in Indonesia, especially from the marine environment and in plants and so forth. And they have these very special properties, but we just need to spend some time characterizing them, figuring out the amino acid sequences, figuring out what the secondary structures are like, and so on and so forth. So now it concludes. So, okay, thank you for listening.
We have some time for questions.
Sure.
Anybody have any burning questions? Yes, Rob
So
has.
I'd like to know if you can build the Eiffel Tower out of spider silk.
No. Because it's crushing. So the soft matter in the silk will just give way, and that goes then to rigidity. You came up with rigidity too early. I was really hoping nobody would say anything about that.
I'd like to ask you about your relationship with the biologists.
Yeah.
When you have a problem like spider silk. It's already been mentioned. Actually, there are tens of thousands of different species of spider that you could go to
Indeed.
and obviously they would have different properties.
Right.
How do you identify, or how do you work with biologists to identify which is the right species?
This is generally quite difficult. Yeah, I work with biologists a lot because I rely on them for the knowledge of biology. So I have a lot of researchers in Gajah Mada University in Indonesia, and they are all biologists, every single one of them. So, I get a lot of info from those guys. Also coming here with Anusia, Rob, and Daya, and so forth. It's like, it's all it's about combining the disciplines, and the only way you can realistically do that is if you work with people who know.
So you go to them with a problem and say, I'm looking for a dragonfly which has a particular...
Well, actually, I'm more random than that, because that's like hypothesis-based research. I just go, I just go with my feelings, and it's like, all right, let's see what happens, and then usually good things happen. So.
But I can give you an example. I mean, one of the things that I was working on was pterosaurs, the big giant flying reptiles. And I was working on the bone structures of these. And most of the time I work on the mid-shaft sections. But in the distal parts of their limb bones, they have very unusual structures. And I gave a seminar in engineering and our engineering department, and I posed this problem that there are very unusual organizational structures in these pterosaur limb bones. And I was astounded that there was no real discussion. And then when I met Parvez, he was here looking at something else, and I asked him about this. And he actually came up with a very reasonable suggestion as to why these struts are designed in this particular way. So, there is a biomechanical explanation for most things, the way they're designed, actually. So, and especially in extinct animals, we don't really fully know everything we can possibly know. But if we have multiple ways in which we look at a problem, often we come to much better solutions, I think.
Absolutely. Yeah. It's all about interdisciplinary stuff. Yes, sir?
I recently saw on the internet there's a solution to your spider silk harvesting problem.
Oh.
There's a group somewhere that's utilizing these slimes from hagfish.
Yes, I know them. Yeah.
It's like it's stronger, but it's mass produced and they can actually make clothing.
Yeah, that's right. Yeah, it's true. And I think they're also bioengineering the hagfish slime as well. We're actually looking at mud skipper slime as well, because this seems to have some sticking property as well. So it seems to help the mud skipper in its climbing, tree climbing endeavors and so forth. But this is a fish. It's not amphibian. It's a fish. It has gills. This is the thing. I mean, it's in the tree, but it has gills. Isn't that weird? Anyway, sorry, yeah.
You talked about nanostructures on geckos.
Yeah.
What size gecko could you have where it would no longer work?
I think it depends. I mean, now you're talking about the weight of the actual animal with respect to the size.
Scale up a little.
So this, I don't know. I don't know the answer to that question. You'd need to.
Pterosaur that acts like a gecko
Might be possible.
You still have larger feet.
It's like the small pterosaurs. Yeah, you need larger feet. But I mean, there will be a specific ratio, I think. I don't know if it'll be linear ratio, but it probably, there would be one. I don't know if anybody's actually studied it in that sense. But yeah, it's a good concept, though. Yeah. Good. There probably has been some people. The people who work with this and who have, there are a lot of people who have actually made. Gecko mimicking, like sticking pads and that kind of stuff. So they probably have already checked this out. So yeah.
Anything else? Any questions?
With biologists, do they normally kind of go through and sort of decide from, like you were saying, the bone structure, this is quite anomalous, I've never seen this before, I can't even classify that as interesting information. A lot of biomimetic stuff, you kind of look at something as mundane as a leaf, and you keep going as a normal thing.
Yeah.
at what point do you go, wow, this is really interesting, let's work on that?
Yeah, well, this is where the interdisciplinary stuff comes in. You see, is if you have a biologist, they have reached a certain threshold. If you have a material scientist, they have reached a certain threshold. But when you put them together, the biologist might say this and that about the leaf, but the material scientist will say, can we look inside it? You see what I mean? And then when we start looking inside it, most material scientists probably want to go closer and to see how far they can go with the structure and try to statistically characterize the microstructure and that kind of stuff. Or maybe chemically characterize the surface or whatever. And these are things that haven't necessarily been done through traditional biological teaching. So this is why, like, mixing is good.
And the other way, you can tell them about the baleen skull and the sperm whale skull. So, I mean, you know, baleen and sperm whales do different things. They have different lifestyle adaptations. And if you look at the bone structures that make up their skeletons, they're different. And so that was a question that we tried to answer. And just looking at the section of the skull, you will immediately see that the way in which the bones are organized is different. And of course, they have different attributes depending on what they're doing. So sperm whales dive to about 3,000 meters, and the way in which their bones are architectured are completely different. So, and then Parvez is now, so I've done the histological analysis, and he has now done the mechanical properties of the bones in those different forms. So it really is a very, very nice way to think about your science. So whatever you do, whether you're working on insects or diatoms or mollusks, but you know, if you see something unusual, there's usually a good reason why they are successful and they have those particular features.
Actually, you can't negate one, actually. This is the interesting thing, because I had done a lot of stuff on the mechanics of these sperm whale skulls, and I sent it to Anusia, and she said, do you want some histological stuff done as well? I said, yeah, let's put it in. So I got that, and then all of a sudden I had to change the entire paper. Yeah? It wasn't what I wanted, you know, but it's what I had to do, because the histology gave a different story. And all of a sudden, things where we were making assumptions or, you know, that kind of stuff, suddenly other things were clicking into position, and we had to write a different paper, actually. But that one's almost finished. You know?
Yes?
What are some of the things you're looking at with your research regarding giraffe fiber?
Well, this is like literally a few days ago that I was, you know, blessed to be included within the giraffe biomechanics group. But I think the best person to answer that question is Rob.
If you look at giraffe skulls, males and females differ radically. Males are huge skulls, they have 35 kilogram skulls on a 2 meter neck, and females have very much smaller skulls. Looking at the bone with Anusia the other day, you know, she said this is very much different. You know, they've got this layering over the top. We know they continue to grow them with age and so on. Then others can come along and say, I sectioned part of it just literally with a hacksaw. And you see all these beautiful little structures inside, which are just like a bit like the Eiffel Tower. You know, it's got a structure here, it's got a curved structure there. These guys can come along and say, this skull has evolved to be relatively lightweight, but very, very strong. Even though it's continuing to grow, the males, as they age, because they're hitting each other very forcefully, and that's another part of the project, very forcefully to win access to females. And they're going to pass that trait on to males and females, their sons and their daughters. So we want to look at the structure from the microfossil to microstructure, to the engineering structure to say how they've evolved. Differences between males and females, I think, is very different. It's a whole new project there. Something, you know, listening to these guys is fascinating. So I just provide the biology. I just sort of film and say, yes, males hit females. Males hit each other, and they hurt each other, and they kill each other. So how do they do it? How did these skulls evolve?
Yeah, actually, what? Right. Actually, watching the video was eye-opening. You know, you wouldn't believe how violent giraffes are. You see them, you know, they look very passive, you know, but they kill each other. They go, it's like a whip. They go, bang, and then they're just bleeding, break. They go for the legs. They try to break each other's legs. You know?
So there's a very nice David Attenborough video on YouTube. You can find that. And if anybody wants to look at Rob Simmons' skull of the giraffe, it's in my office, so you're welcome to come and have a look at it. Its internal structure is nothing like any other mammal, so it's really very, very unusual. So, okay, I think we have to stop. So
Okay.
thank you all very much. And
Okay.
thank you.